Okay, so this is section 1.10. We're going to compare some real numbers. So we're going back to that section 1 we did in the very first week where we looked at the rational numbers kind of graphic organizer here. So this one was already filled in week 1, so I'm not making you refill this part back out. What I want to do is add the irrational numbers section, because any number that can't be written as a fraction would come over here to the irrational part. So this is any number that cannot be written as a fraction. So make sure you fill that label in there. And we have some examples. Let's see if it'll come up. So a square root of any non-perfect square. So we kind of already talked about that in some of the previous videos. So a perfect square would be like 2 times 2 is 4. 4 is a perfect square. 8 times 8 is 64. 64 is a perfect square. So those are rational numbers. But if you take the square root of a non-perfect square, like say, what's the square root of 26? That's going to be an irrational number. It's going to continue on and on and on forever. The decimal will not terminate. It will not repeat. It will just continue on and on forever with no pattern to it. So that's a non-perfect square. So that being said, I want to throw in here that the square root of a perfect square is an integer. That is a rational number. So we do have both of those two that come up. Decimals that are neither terminating nor repeating, so that's that idea. That's why a non-perfect square, when we take the square root of it, is irrational. So we can kind of see I did pi here. So this is pi, and it's just the first so many digits. I didn't even count how many digits I did. But it will just keep going on and on and on forever. It never ends. And so 3.14 is what we normally use for, but that doesn't mean it actually terminates on 3.14. It just keeps going on and on and on forever. So this is one of those very irrational numbers that we see quite a bit in math. All right. So now that we have kind of that idea, what we're going to do is we're going to go through and we're going to start to identify whether or not a number is rational or irrational. And let's see, I think we're going to do whether or not it's an integer. So we're going to do a couple of different pieces here. So we'll see that on the next page. One thing I thought was fun, this is a fun little game that you can click on if you just search for pi, P-I, on Google Chrome. And then you can click on this sparkly little blue piece, so I can kind of play it again so you can see the little sparkly. It's a little memory game that you could play. So it'll test you on the digits of pi. So it'll start with 3.14, and then the next round will have the 1, and the next round will have the 5. So it's like a little memory game. I don't know. I thought it was kind of fun. So just so that you know it's there. So you just have to click on the little sparkly part here, and then it'll play a game. I'll go to the next one. Okay, so I'm circling this just so you know this is the one we're going to work on first because there's 4 different problems here. Ignore that down there. I forgot to animate that, so I'll animate that in a moment. All right, so it should disappear now. Oh, darn it. So classify each number below as an integer or not. So remember an integer, if I kind of back up here, an integer, we have these different layers of rational numbers. So natural numbers are counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, but there's no decimals. Whole numbers are counting numbers and 0. Integers are the counting numbers, their opposites and 0. So it's positives, negatives, and zeros, but again, no decimals here. It's just whole numbers as far as, I know I'm saying whole here and then whole again in a different way, but whole numbers is in like there's no partial numbers. That's what a decimal or fraction represents. Although rational numbers, that's the blanket for all of these categories, is any number that can be written as a fraction. So if it's already in a fraction, that's rational. If you see a terminating decimal, so it just ends, 0.65 is an example, that is a rational number. Or if it's a repeating decimal, so you have a little bar notation, or sometimes you might see ... saying that it's continuing with that number. That can be a little misleading because you can see ... here at the end of pi. That does not mean the 9s are repeating. So just be a little careful with that notation. Usually there's a bar. But a repeating decimal can also be written as a fraction. We practiced that back in section 2, I believe. Maybe section 1, actually. So if you don't remember those things, go back and practice them again. Watch those videos so that you can kind of see how they work together. Ooh. Okay, so this is written as a fraction. 15 divided by 3, though, I already know 15 divided by 3 is 5. I can reduce that down to one number. and that fits in natural whole numbers and integers. So that would go all the way up to integer because it's just a 5. There's no decimal place after it. So it's definitely rational because it's already a fraction, but it's an integer because there's no decimal. Negative 54, no decimal, so that is also a fraction. Or, geez Louise, also an integer. I'm losing my words here. We see a decimal place here, so this is not an integer because it has a decimal. 20 divided by 17, if you actually did the division here, you'd get a funky decimal that goes on and on forever. So this is not an integer. It's not even rational. This would be irrational. And then I can also see another decimal here, so this would be a no. It has a decimal. So this is just simple. Does it have a decimal or does it not have a decimal? All right, so the next one, rational or irrational. So pi was one of those ones. It's always irrational because it's that number that goes on and on and on forever. 16, so if I take the square root of 16, it's a perfect square because 4 times 4 is 16. So since it's a perfect square, it is rational. 3 would be fine, but the square root of 3, that's a square root of a non-perfect square, so that makes it irrational. And then negative 6 over 5, that's written as a fraction, so that is immediately rational. If you can write it as a fraction, it's a rational number. And then here, this shows 43, negative 43.17 with a bar over it, so it's repeating. Repeating decimals are rational. Hint, so are terminating decimals because both can be written as a fraction. So that was the part that wasn't animated quite yet, but it is rational. All right, so now we're going to come up here to this one. And we're just going to determine if it can be written as a fraction. So we're just practicing that again. So remember, if it's terminating, if it stops, then yes, it can be written as a fraction. So because it's terminating. So terminating can be written as a fraction and repeating can be written as a fraction. Again, if you don't remember that, go back to section 1 videos. I have a terminating decimal video and a repeating decimal video, so you can watch through that to remember how to do those things. So here I have a repeating decimal. So yes, because it's repeating. This is not a great way to put this, but this also means it's repeating. I don't like it when they use the dot, 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 because that could be misleading. But in this case, they are showing that the 5s are going to continue, so that is repeating. This is also dot, 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 but I don't see any kind of pattern before the dot, 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 so it just means it keeps going, but there's no pattern to it. So this would be a no, because it's neither terminating or repeating. So it has to be a terminating decimal. It has to stop, just like 0.92, or it has to be repeating with a little bar notation. They could use the dot, 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 but I prefer the bar notation because it's a little more proper to show that it's repeating. It needs to be one of those two to write it in a fraction. All right, and then the last piece here, what we're going to do is we're going to order these numbers from least to greatest. So the first thing that I think we should do is turn these into decimals because they're easier to compare if they're all the same type of number. So we're going to just turn each one into a decimal. These two, the second one and the fourth one, are already decimals. We just have to turn the first one and the third one into decimals really quick. So we're going to divide 157 by 20. So we get negative 7.85 because there was a negative in front, so make sure you put the negative. This next one is already done. It's negative 7.64, so I just brought it down. The square root of 50, so we use our calculator. You type 50 and hit the square root button, and you get 7.07. And I do believe I rounded that. And then negative 7.6 is already a decimal form. So now I'm just going to put them over here so that we can line them up and see. You just want to make sure, and I by chance put them in order already, but you can line them up out of order just to help you, because what you're looking for when you're saying from least to greatest is, since all these 7s, they don't all match actually, right? 7, that's positive 7, that's bigger than all these negatives. So 7.07 is my biggest number. That's going to go on the very end. That's my greatest. So now I'm going to just focus on these 3 negatives. I'm going to ignore the negative 7. I'm going to move to the next number. 8, 6, and 6. So 6 is smaller than 8, so let's focus on 6 and 6, which also tells me that 8 is going to be the second to last number because it's bigger. So I would have 0.85 and then I'd have this 0.7. So I just need to decide which order these are going in. So remember, this means that it's 6, 6, 6, 6, 6, 6, 6. That 6 is repeating forever and ever and ever. So we have 6-4 or 6-6. Which one's smaller? Well, 6-4, right? So 6-4 would go next, and then 6-6 would go after that. Well, I actually kind of fibbed there, didn't I? They're negatives. So what this actually tells us, the bigger the number, the smaller it actually is, because it's negative. So I wasn't paying attention to the fact that they were negative at first when I was explaining that. I do have them in the correct order here. So it would be negative 7.85, that's the smallest number, then negative 7.6 with a bar repeating, then negative 7.64, and then 7.07. So these are in order from least to greatest. All right, so that was, I think, the last section of chapter 1 where we're comparing real numbers. I hope that helped, and I will see you in the next video.